All right, so welcome everyone to another OCP Tap call. This is call number 118. Today we have Paul Borrill giving us a presentation about timeout and retry, TAR, in distributed systems. Paul is a chief product officer at DÆDÆLUS and an expert on software infrastructure. He contributed to system development at NASA, Sun Microsystems, Quantum, VERITAS, and Apple. Paul co-founded the IEEE Hot Interconnects Symposium and the Storage Network Industry Association. Paul earned a PhD in physics from University College London. He's also a founder of ItsAboutTime.club, for a forum for physicists, computer scientists, mathematicians, neuroscientists, philosophers, and practicing engineers to explore our unfolding knowledge of the nature of time and causality. So with no further ado, Paul, the floor is yours.
Okay, well, thank you, Ahmed, for inviting me, and thank you, everyone, for coming and lending me your ears for the next hour. So as Ahmed said, I'm Paul Borrill, and as given my background, what he didn't say was that my obsession with dependable computing started when I put an experiment on the last successful flight of the Space Shuttle Challenger. I'm now on my third company, determined to realize a vision for simple, reliable, and secure software infrastructure. In my previous presentations earlier this year were episode 1, which is the what, about time, episode 2, the why, and episode 3, the how. This is episode 4. We call it timeout and retry, or TAR, in distributed systems. And we're going to delve into the notions of instants and intervals and show that instants aren't helpful in causal ordering, and that even intervals defined by timestamps on different timelines are problematic. So failures caused typically by dropped, reordered, duplicated, and delayed packets cascade into timeout storms and in networks and reconstruction storms in storage. This results in metastable failures, sometimes called limp-ware or gray failure. This is important because we see silent corruption of data structures, even in small clusters. So today I'm going to review what we know about instants and intervals and timeouts and retries. And we'll also try to get to a review of the latest November 2024 SOSP paper, which the folks at the University of Chicago and Microsoft very kindly put out to illuminate this problem for you in a spirit of exploration and collaboration. So I'm going to ask you to give me a 20-minute head start, and then feel free to ask questions. So what I'm hoping to be the takeaways for today's talk: time can be disseminated, but only with statistical guarantees. There is no certainty. The only thing that is certain is that clocks drift apart without bound. So see the excellent talk by Mark Weiss earlier this week on OCP TAP on Monday. We assert that reliable transactions require multi-way synchronization. And distance simultaneity, or one-way timestamps, are an unsafe ordering construct. The problem is that instants are meaningless. Only intervals on the same timeline are actually relevant. Photons don't carry timestamps, but timestamps are carried by photons. The speed of light is the pivot around which time and space evolve. And timeout and retry on different timelines will silently corrupt data structures. One of the things that you might find also very interesting as we delve into the technicalities of this is that Shannon entropy, if you remember, is a logarithm, and the logarithm of 0 is minus infinity. So measurements appear to be instantaneous only because there is no background of time on which to measure anything. Timestamps don't help with causal order. So I'm not going to read the rest of that slide to you. I'm just going to move on and get to the meat of the matter here. So let's quickly review some of the basic tenets of distributed systems. This includes safety, which is nothing bad will happen, and liveness, which is something good will eventually happen. Problems occur when packets get dropped, reordered, duplicated, or delayed, and software has to intervene to fix an impossible problem after the Shannon information has been discarded in the lower network layers. So our argument is that drop packets destroy causal order determinacy, that reordered packets require unbounded reordering buffers. Well, then we run into the discarding and forgetting problem in quantum mechanics and lost Shannon packets, and that duplicated packets destroy non-idempotent data structures. And unfortunately, most data structures in databases, for example, are not idempotent. Delayed packets are the ones that cause timeouts as well, causing more retries. So you get the idea. There's a big problem here that we haven't yet solved in all the decades of work that we've done in distributed systems. So let's just talk about this thing called entropy. If you remember Shannon's famous formula for entropy, we can go into this quite deeply, but I'd rather do this in my presentation in January and stick to the events on an interval of a single timeline here causing this timeout problem. So in Shannon's famous formula, the logarithm of 1 is 0, and the logarithm of 0 is minus infinity. And so in a Shannon channel, like on Ethernet, where Alice and Bob are exchanging information to any protocol you want to, without a background of time, a photon is just an arrival event. And a bunch of photons arriving, which is what you get in an Ethernet channel, is just a whole bunch of photons that crosses the threshold of the receiver so that you can record it as being the SERDES can record it as being received. So we'll give a full presentation of the life of a photon in our presentation on the 1st of January, which is less than a month from now. And we've called that Ethernet spacetime. So one of the things that we know is that an alternating bit protocol, which with ACKS, is the fastest possible way to resolve the uncertainty. And it will show up as not being able to measure or depend on the one-way speed of light. So this, unfortunately, converting my slides from white to black here missed out the axes. You can very faintly see them in the X and Y direction on this, but this is just a logarithm on Mathematica. But when we do the reflection of this and say, well, what does Bob see and what does Alice see? You end up seeing this. You end up seeing that they both have this no man's land in the middle, which is where all the problems occur. And Einstein had a really nice quote on this, which I think I've got somewhere, which I'll try to describe. So, okay, here's the key problem. It's impossible to calculate intervals on a Minkowski background because the coordinate system of the emitter and the observer are inaccessible. They exist only in our imagination. And attempts to create a background using NTP, PTP, White Rabbit, or Sinky are doomed to fail. This style of thinking misleads us about the nature of causality in our algorithms and prevents us from building reliable distributed systems. And what I mean by reliable is those that don't silently lose or corrupt data structures, at least not without warning us explicitly that the atomicity assumptions in our subtransaction sequences were violated. So on the left-hand side of this, you can see that I've taken this thing that Einstein did in his famous paper in 1905, and I actually talked about the path, which is the distance, and the interval of time at the bottom. And notice that when we do that, we get a pivot. The C is a constant. It's a constant of the universe. So it turns out that the distance divided by time is basically a pivot around which the universe evolves and unfolds. So if we just do that, let's say just a standard algebraic quantity, so we're not getting confused by distance and time. So if you had an A divided by B, what we can show here is that this is a problem because first of all, we don't know how far the photon has come. There are no Minkowski manifold coordinates transmitted along with the photon. And we don't know where we are in this Minkowski space-time, even though we can invent TAI. That's another man-made illusion that we try to create. But the thing at the bottom here, that in classical mechanics, that could be anywhere from 0 to infinity too. But in relativity, we know for certain that that's zero, because the time that a photon experiences is zero. So I'm going to read this actually on the slide here. I'm going to do the forbidden thing. There are no Minkowski manifold coordinates received by the observer or the detector. All we have is the arrival of information which contains wavelength and contains polarization and phase. And we'll get to this later, or at the next session in January. What we do is we average photons over intervals of time defined by the observer, not by the emitter. And so the bottom line here is it's impossible to calculate intervals on a Minkowski background because the coordinate system of the emitter and the observer are inaccessible. They exist only in our imagination. So this logarithm of zero thing, which I showed you a moment ago, it basically says that there is no background of time, that you can measure things that are transitioning from one arrival event to another arrival event. And what we're going to do is show that that can be turned around in physics any way we wish. We can reflect it, we can rotate it, we can give it parity reflections, which is what you see in a mirror. In physics, by the way, the CPT symmetries in physics, which is charge, parity, and time. We don't worry about charge because photons don't have charge. And we don't need to worry about mass because photons don't have mass, but they do have time and parity. So it turns out all the mathematical operations on there will give us this operation, which will take us through this operation. So what I'm saying here is that there is a causal diamond in the middle here, and that's how we kind of relate to what's going on inside a general relativity. So I'm going to give you a bit of an overview here of how we get from quantum mechanics to general relativity. And basically what we're going to do is replace those causal diamonds in relativity with causal squares. The reason why we're going to do this is because this, I think, is going to illuminate the problem of why we can't have nice things in distributed systems. I can hear some sound in the background. Could whoever's got their microphone open, could you please mute? Thank you. So here's the problem. Photons don't carry timestamps. So how can we assign a meaning to timestamps when Einstein's special relativity denies the existence of distance simultaneity? So later in this talk, I will talk about the life of a photon. But basically, the issue is this. Photons don't carry timestamps. So we've got the situation here of the light path of a time interval. By the way, those are the words used in Einstein's original paper. Can either be, a delta or a differential. Either way, it can be infinity divided by infinity, or it can be 0 divided by infinity, or it can be 0 divided by 0. The point is, when we do this from a Shannon channel perspective, these things are all undefined. And so taking the limit from the positive direction, p log p, yields a different answer than taking the limit from a negative direction. So let's take a look at this thing that you'll notice on here, that in general relativity, the notion of a causal diamond is basically what everyone talks about in a Minkowski background. The paper here is from Edward Witten. It's on the archive. He gave a fantastic paper. It's actually a tutorial on light rays, singularities, and all that. Thoroughly recommend that you look at it. There's another great paper called The Experimental Evidence That a Photon Can Spend a Negative Amount of Time in an Atom Cloud. This one is very recent. It's only just been published in the last month or so, I think. So the point is, without going through all the details here, photons can spend negative time in an atom cloud. Isn't that amazing? So that kind of like puts kibosh on a classical, not classically, a relativistic view of space-time from Einstein, and particularly in general relativity. So what I'm going to try and show is that the causal square here is all made up of a photon clock. What I've got is two mirrors, one on either side, and we're going to bounce photons backwards and forwards inside of there and see what happens. So I hope you've already got the message here. Maybe this is the fifth time I've said this. Photons don't carry timestamps. So we're going to basically say, we've got these two mirrors here and here, and from outside the mirrors, some photon enters from the universe. Imagine, this is a detector or a mirror in the actually it is a mirror in the James Webb telescope. Comes in from the beginning of the universe, 13.7 billion light years old or something, and it's coming in, say, from infinity. When it arrives, hits the mirror, and then it can go backwards and forwards between the mirror and the detector until it's finally absorbed. It doesn't necessarily get absorbed on the first time. But then what happens is once it's stuck bouncing between two mirrors, let's imagine these are perfect mirrors. And by the way, the 45 degrees is really just, the speed of light is 1, and it's a 45-degree angle is the same as light cones. So what we're seeing here is that photon can get trapped. It can get trapped, and it's outside of normal time that we call time, and it's in some kind of subtime where the photon bounces backwards and forwards forever without having any epistemological effect on the world. And then something happens, and something disturbs the system, and this photon exits. And let's imagine it's just probabilistically getting absorbed by the detector instead of reflected from the detector. And there's plenty of math on this. I'm not going to show it in the presentation today, but this will give you an idea that bouncing photons backwards and forwards basically don't use time. They don't show up on any kind of timeline that you might have. But once the photon exits, I call that a Hilbert photon. It can go off into the universe and go and search for somewhere else to go and play for a while. So this is a wonderful paper by what's his name now? So this is okay. This is I'll put the references in the last slide when we send it out after this talk. So there's an idea of what's going on. If we have Alice and Bob, then we can define with a Pythagorean kind of theorem, we can define C. We might not know what C is, which here does actually happen to be the distance between one end of the event and the other end of the event. But what happens is this is an inertial frame, and we can define this X and not X, and then we can take a look at what this delta might be in the middle, depending upon the velocity of Alice and the velocity of Bob. So when we do that, we get this particular effect. Notice it's gotten bigger, or this particular effect. So what happens is this completely accounts for special relativity in this nice picture, which Duguid helped me draw in Mathematica. But what happens is we have this red line here. It's like, well, what is that red line? Who put it that way? And why is the arrow at that direction instead of this direction? We can ask questions, from first principles, like, well, is this a photon coming from Bob, to Alice and arriving at Alice? It turns out that these things can be the opposite way too. Whoops, that's the wrong way. Can be the opposite way too. It could be a photon coming from Alice going to Bob. And now we have to say, well, okay, these are all symmetric counterfactuals in any theory that we need to come up with. So the trouble with having this God's eye view is because we don't see a God's eye view as an observer or a detector. We only see a local observer view. And both in general relativity and quantum mechanics, they impose this human invented background of time. And this includes the direction of time, which is nothing more than the direction of information transfer. This is where we're going to connect this into the Ethernet cavity, which we'll talk about later. So is it going from Alice to Bob, or is it going from Bob to Alice? Well, when it comes to causality, only a local observer view works, and where we can account for the internal events that can't be seen from the outside. These are hidden. So in the eye of the observer, who is the observer? Is the photon the observer? I don't think so. But we do know that the proper time for a photon is 0. Is it the transmitter? Is that the observer? where the transmitter's sent something and it's discarded the information that it has, it no longer remembers that it sent it, unless you keep a special buffer and logs and everything else about what you've sent. Is the receiver the observer? Well, probably, because the receiver is receiving new information. It's like the information content, the resolution of uncertainty is getting better. So this thing is going to give us this photons bouncing between those mirrors, carry shared mutual information between Alice and Bob. And until this information is captured, which means it turned into knowledge or memory, there is no evolution that can be called time. The photon capture is timeless. When this information is captured, the photon energy is captured by the receiver in memory. We do this in our registers, in our smart NICs, and we do it in our memory, in our computers. But it's no longer available to be shared in this ping pong between Alice and Bob in this hidden variables kind of view of the world. So anyway, I'm not going to have my animations were proper and possibly done there. So it's impossible to synchronize clocks in principle. It will therefore be problematic in practice. And that's what we found. Clocks basically drift away from each other without bound, unless you synchronize them. Clock synchronization error is indistinguishable from one-way latency. This is what Edward Lee basically taught us in Mulligan Stew. And I finally understood that he was maintaining a one-way latency and not a two-way latency. But we still know that the direction of causality is stochastic. So we're going to talk about this in our next description in the next talk. So when experiments try to measure a one-way latency, such as in belt state or entanglement measurements, they are committing them in cascade error, which is basically assuming this block time that is a real thing, and it's not real. It's only in our imagination. When computer scientists imagine they can assume a background for one-way latency, they will find that there are no completions that are necessary to create the two-way nature of this theory. So things like monotonicity, for example, is in the eye of the observer, but that's not how space-time works. And no amount of recovery code will save you. So we talked about general relativity, time goes from past to future. Why can't we just flip these things around? Why is it that we have to have this kind of view that we impose this direction on the background of time, both in quantum mechanics, which is here. This is a Feynman diagram. Time goes up on this, by the way. You'll notice. Well, who ordered that? Time in quantum theory is a parameter. First, you do the experiment, and then you look at your watch. So this is just as much nonsense as in the general relativity case, where we impose a direction of the light cone from outside of our human perception. So we can get big causal effects that we can say there are space-like and time-like things in this Minkowski's theory. Doesn't really work very well. We can look at what Lamport, for example, talks about in his process, in his definite causal order. And what we're going to talk about is this alternating causality. What if this ping-ponging of photons, which is timeless, goes on between these perfect mirrors? Then what happens is we've got two light cones back to back on each other, and we can just go ahead and spin them around any amount we want. This is just another example of how do we go back to the fundamentals of what these symmetries are in our mathematics and physics of general relativity and of quantum mechanics. So here are the fundamentals. Probability in a Shannon channel is information, and or entropy is the lack of information. So what does probability 1 mean? What does negative probability mean? What does complex probability mean? Because in quantum mechanics, in fact, in all, even classical probability, you can actually have a series of equations that have a negative probability somewhere in the derivation, and then they magically disappear by the time you get to the thing that you really want to observe. This is all well known. It's true in both classical mechanics as well as in quantum mechanics. So then the question comes in, how does Bayesian probability enter into this? Well, Bayesian probability has to have a prior. If you have a prior, what are you assuming? Are you assuming the photon arrived from, the infinite distance in the universe on this James Webb Telescope detector, or are you assuming it came from, another motherboard of the same computer, or in a network in the same data center a few hundred meters away, or many tens or thousands or hundreds of or thousands of kilometers away across the internet. So this is why we have to think very carefully about what we're assuming is our prior in a Shannon channel. And one of the things I'd like to do now is we've talked about how this works in the causal diamond. What you can see here is, the mathematical description I've created to manage this this question about what do these arrows mean when you can build these triangles. For example, when Alice receives this from the universe, she has no idea what a triangle is. Everything is infinite in uncertainty. But by the time Alice sends something to Bob, Bob now knows that Alice exists, but Alice doesn't know that Bob exists. But if Bob responds by reflecting it back to Alice, then Alice now knows that Bob exists. And then when she reflects it back to Bob, we have a complete I know that you know that I know, which is the mutual information in Shannon theory, and also in computer science. We also have a notion of mutual information, which I'm hoping myself and someone else will go into in a future session on OTP. So let's say, okay, so let's shift gears now and let's see what's going on. We're almost halfway through the time here. It's 29 minutes past. So in November the 4th, which is exactly a month ago, there was a great paper there all about timeouts and retries. So if at first you don't succeed, try again. Now this is a wonderful piece of engineering. It's an excellent classical way of thinking about time and how to deal with the uncertainty of these timeouts. The re-execution of task failure is a common mechanism to enable resilient software systems. Everybody wants resiliency. We want things to work. I don't know about the rest of you, but I get really annoyed by things that don't work. Yet, despite its commonality and long history, retry remains difficult to implement and test. I thoroughly recommend that you go ahead and find that paper and read it. Here is my take on this. They don't say this in the paper. So this is Paul Borrill's take. Timeouts and retry is the root of all evil in distributed systems. So what else do we get from this? So if at first you don't succeed, this is what they're finding. They've got all of these applications that were studied, and they found a whole bunch of bugs. They found the retry. They call them retry bugs now, and they're peeling the onion and trying to find out what's inside and have different categories or subcategories of different kinds of bugs. This is great engineering. So I'm very proud of these guys for having done this, and I'd like to use some of their theory and particularly their validation about the problem to be able to move the ball forward on understanding this problem of timeouts and retries. So the point is, these retry bugs aren't a bug in the code. I'm saying it's a bug in our assumptions. Because if we've got false, positives, which is timeout too soon, this causes unnecessary smash and restart of the Shannon information, and it causes, overloading of the network, which leads to, if everyone does this about the same time, then you end up with cascade failures that cause all sorts of problems. And false negatives, basically cause slowdowns and limp-ware and gray failure. And these days, I think the term is metastable failure. But don't forget, once you get this metastable failure going on with retries, you're going to get corrupted data structures unless you're extremely careful about the way that you treat time and you are looking on a single timeline on one computer. This is the words that Edward uses, which I really like to encourage, is really make sure you've got the timeline for what you're doing your retries on your computer, and don't, and we've got the great some great work done in the Intel processor these days called TPM, which this community knows all about. The bottom line, though, unfortunately, is orchestrating retries isn't going to save us. I had that in the last presentation about orchestration of retries. Another great paper. I'll put it in the references for this as well. But the common practice in all the large cloud companies is randomizing retries. And that just, kicks the can down the road. It doesn't solve the problem. It just makes it less frequent and when these really bad storms start to happen. So the problem is cancellation isn't going to save us unless we can reversibly retrieve any not yet captured information. So if we have in the retry code that we try to get going, rather than just reset everything in all the SmartNICs and all the memories and all the caches and buffers and everything to zero, if we can kind of retrieve, hey, tell me about the work that you've already done. How far are you through that transaction? Did you complete it? Did you not start it yet? Or are you in the middle of a two-phase commit, for example, when I need to retrieve from you the idea that that was a forward in time operation that I'd like you to do for me. So this is all good stuff. And, we can talk about back-to-back Shannon channels. We can talk about this causal island diamond or causal box. This is what's going on in that. And also we can talk about the logarithm of zero, which means that there is no background of time. And so what I'd like to do is open the floor right now and talk about this and ask any questions, by the way, about this paper from Microsoft on the background of time. So let me put this up here so I can see everyone in the. Let me just say. There you go. All right. So is there anyone brave enough to ask any questions? I've left lots of time.
Oh, I have a quick question. Are the retries for like a single packet retry, or is it for multiple packets or, one packet within a flow? What exactly is the retry here?
So what's happening in the quantum world, which is actually coming up at this problem from the other side of the world, is they're talking about the information being lost by being discarded, or in the case of machine learning, forgotten. In fact, we had a whole talk here on OCP TAP from the fellow who's a professor at UC Santa Cruz, basically talking about forgetting of information in his machine learning infrastructures. But quantum mechanics these days are actually all talking about discarding. And in fact, there's some great papers by some very wonderful physicists on the archive recently about this discarding problem. So Dan, to answer your question, anything which is unintentionally discarded will cause these problems. So if you want to discard something, you basically ought to go back to the source and say, okay, you've told me when is it safe to discard? It's never safe to discard something in the middle of a two-phase commit. For example, there's lots of other examples, but that's the one that's the easiest to understand. So if any packet is dropped by an intermediate switch, for example, or even by the NIC. The NICs are also, if they can't push the data fast enough into the memory hierarchy of the machine, then the NICs have to drop packets too, because the next one's coming in. There's nothing else you can do in a smart NIC. We either forward it to somewhere else, push it up past the PCIe bus into the main memory and say it's yours now. Do something with it, or drop it. Those are the only choices. So dropping these packets is basically a protocol issue. And so when I talk about, for example, two-phase commit or doing, that's basically two lots of sends and acknowledges, there's 4 messages. But there's a very simpler version, just doing a simple RPC, which is send, do something, and receive. That closure has to happen. And there's no reason why that closure can't happen on every single link. Some older protocols actually do that, but the modern problem is that the only thing that the switch vendors have got to sell is bandwidth. So the answer to every problem is bandwidth. It's like, oh, you've got cascade failures and Well, obviously you need more bandwidth, so let's sell you more expensive switches. And oh, you've got this tail latency problem. Well, let's spray the packets over many more paths, and then let the destination sort the mess out at the end. All of that does is makes things worse. So the problem is timeouts and retries, and you can't answer it with more bandwidth, because more bandwidth and overloading a network will basically keep on banging into this wall, our heads against this problem. So Dan, did I answer your question?
Oh, yes, but what would you like to see the switch vendors do?
I'd like to
Or
get
what?
out of the way. I'd like to switch. I'd like to have the SmartNICs talking to each other directly. Now, the reality is, the switch vendors have a very dominant market position, so they wouldn't even let us in the front door. But we can build mesh networks very easily for example, in a chiplet kind of system. This is what Google is already doing with their TPUs. It's in a kind of like an orthogonal mesh. Same as what Dojo in Tesla and Elon Musk's AI infrastructure. That's also a mesh, a square mesh. The switches and the routers are really like outside of that environment. It's easy to see where this is going for a chiplet economy. You really want the switches and routers and the existing infrastructure, which you have to be compatible with in order to get something to go to market. That is outside of this area. So once we've shown how well this works between nodes, in a small mesh network, it's easy to say, well, that protocol can be used, for any for between the switches too. And yes, it will work between the switches, but I'm not going to hold my breath for the switch vendors to get this particular problem about lost Shannon information, because they'll drag their feet because they're trying to sell more of what they've already got, which is bandwidth.
I
Thank
just
you.
want to add something, Paul, to what you said. So I totally agree. Timeouts and retry is the root of all evil in distributed systems, because there is no time for at these speeds, right? Like it's like there's no time for timeouts and retries, right? And more importantly, it's the tail latency problem, which is the jitter introduced in the system, which kills all scalability that we cannot afford, right? And that's something that Van Jacobson describes really well, that in a distributed system, it's not so much the latency, it's the jitter, which is the biggest problem for scalability, right? So yeah, I mean, definitely this is the root of all evil. I agree.
Excellent. All right. Well, this is a good discussion. I wanted to do this. I wanted to promote more of a free-flowing discussion around these topics, because there's a lot of knowledge and expertise out there for how these problems have been addressed in a conventional way. But I'm basically saying that with a small change in perspective and how protocols work at layer 2, for example, we can make sure that the Shannon paired information isn't lost. By making it, basically go link by link. Now, if your link is between here, on the moon, or here and Singapore, for example, you really don't want to wait the round trip latency before you send the next packet. I mean, this is the simplistic way of looking at it. This is called credit-based flow control, as you know very well, Anjali. But what you do get, though, is if you're inside a single rack, then all of your cables are no longer than your arm, and that's, if you calculate at like 100 gigabits, the actual latency of a 64-byte packet, it feels like, that the length of your arm inside a rack. So can you imagine what happens when we start to go to the next level of miniaturization in chiplets? Almost every packet is going to have its head in the receiver and its tail still in the sender as it's transmitting things. So there's no reason to think that you have to stuff the channel with packets as fast as you can. You can actually do all of the flow control much more easily if you're working within a single rack or in a single motherboard for chiplets.
So Paul, I have a question. I'm I didn't understand your connection with entropy and Shannon information, because the P in the logarithm is a probability, not a time.
Yes.
And the logarithm is multiplied by P. So it's P times log of P for the entropy. And 0 times the log of 0 is 0, actually. So there's not really a problem with a probability of 0. It just reflects the fact that there's no information in, if you observe an event that has, well, if you have an event with probability 0 and you observe it, presumably it won't occur because the probability is 0. So there's no information conveyed because you already knew that it wouldn't occur.
Okay.
I don't get the connection there.
Okay, this is really kind of like the hard part. What I discovered, I'm actually sharing a house with a mathematician, so I get to talk about this stuff, and every time I discover it and do the research. There's a wonderful series of papers by a mathematician in Europe who has basically dug into all of the assumptions, like, is anything multiplied by 0 always 0? Is 0 divided by 0, for example, always 1? Because anything divided by itself is supposed to be 1. These are conventions in mathematics. And it shocks me to find out that this is a very, let's say, a controversial subject amongst mathematicians. If you go onto the internet, you'll find that all of these discussions, you can even have a therapy session with ChatGPT on this, if you'd like. But basically, this combination of zeros and infinities don't give you zeros and ones all the time. The issue with P log P in Shannon information is, are you approaching it from the negative side, or are you approaching it from the positive side? Because that basically says whether or not these conventionally accepted notions are true or not. So what I've realized is something really quite interesting. It's and I think I said this earlier on in here without actually you seeing it. It's let me bring it here. What we've done is we basically said, okay, if I've got a photon that arrives and I've got distance divided by time is a constant, that's the speed of light, then I've got 0 and infinity are like on the top of the equation and on the bottom of the equation. This is the A divided by B algebraic description. But what I did is digging deeper into Shannon information theory, and I've got 3 Shannon binders, by the way, besides my desk here. I've got everything that, not everything, but probably 90% of what most of people have written. So what I realized is we need a set. The set is minus infinity, -1, -0, +0, +1, and plus infinity. Now, notice that the new way of looking at this thing here is I listen to an awful lot of mathematician videos about how you do algebra, and all of this stuff comes up in that. And this was in the last 3 months. But what I realized is that the thing that gets me out of trouble is being able to define -0 and +0, because then when I take the limit, I can end up with a negative number or a positive number. Because if I add, if I have an additive algebra, which means that if I've got something that's already negative, I do the additive thing and it becomes more negative. If I have something that's already positive and I do the additive thing, it becomes more positive. And so what I'm grateful for is that some of the conversations I've been able to have with Dugan about this, and some other folks, where we realized that when we plug this into the P log P formula, you get this undefined behavior, which seems to be a clue as to what's going on in the difference of perceptions between general relativity and quantum theory. And it's not quantum theory, it's really Shannon information theory. So did I answer your question?
Not really. I mean, when you're talking about the information theory, you're talking about probabilities, and I didn't get the connection between these probabilities and time.
The next presentation I'm giving in January is basically going to go into the Shannon channel. So, for example, a one-way Shannon channel is the way that we normally think about information. For example, and we can tie this into how time works. If we're transmitting from a GPS satellite, you're getting correlations. The vast number of photons that is coming down on Earth, are being, you're only getting a tiny, tiny number in your iPhone to figure out where you are in time. That's kind of dissemination of time. The GPS satellite has no idea that you're listening. And the Shannon problem there is that you can broadcast to your heart's content, but with this one-way Shannon channel style of thinking, you end up with the wonderful technology we have right now, which is broadcast, and not just of TV and radio, but also of GPS and time. So what I realized is when we investigate the hierarchy for time synchronization inside PTP, I realized that well, we all know that GNSS is vulnerable to spoofing and other nasty things. But what I realized a long time ago, and which I'm trying to find a way to express here, is that synchronization does work, but you have to have a hierarchy. I'll say it in a simple way. All time is a tree. You just have to pick your root. And what has happened, I think, empirically in the engineering community is they've all discovered that. That's the only thing that works is you pick a root, a grandmaster, and you tell everyone else to be synchronized to me, and I'll make sure that you're ticking in lockstep to me. But then, of course, you have to compute all of the delays between the switches and the internal delays in the switches. And there's lots and lots of engineering that can kind of cut that down and minimize the error, so that clock synchronization error is the smallest. But what I'm trying to say is there's a certain coherency here from the grandmaster. If it's not connected to GNSS and it's not being, quote, disciplined, as soon as you discipline a clock, all bets are off. Your coherency, your causality is just going to go through the roof. But if you keep one of them really stable, your grandmaster, then it can kind of give a very coherent ordered set of timestamps to all of the other nodes, and that's going to help a lot. The big problem there, of course, is that if that fails, you've got a single point failure. So now the next problem in engineering comes, well, how do you fail over between different grandmaster clocks? For example, in a large data center, you might have 2 or 4 or 8 or more grandmaster clocks. And I heard from Kevin Stanton, who's actually here today. He taught us something wonderful in our Lake Tahoe offsite in June, that you can have up to 256 of these, which is great, because now you've got 256 possible routes. So the engineering challenge simply becomes, well, okay, how do you use these as a tool set? Can I, for example, synchronize the whole data center from one grandmaster, and then if something fails, we have to fail over everybody to the next grandmaster? Or can you use these up to 256 grandmaster routes as separate fiefdoms, as separate synchronization domains for different tenants, perhaps, inside the data center? So I think there's some really great engineering we can do here by taking the wonderful tool sets and protocols and engineering that's been done in the PCP hierarchy, and then trying to capture and utilize them to make distributed systems more reliable. Did that better as an answer, Edward?
Well, I think I get the intuition. I have one more question. I mean, I think you made a very convincing case about the answer to your question, how can we assign meanings to timestamps? And I think what you said is, don't try to assign a meaning to a timestamp that is the time at which something occurred. I think you make a case for that. But there's another meaning you could assign to timestamps, which is a pretty useful practical one, which is not the time at which something occurred, but the reading on my local clock when the something occurred at my location. Right? That's another meaning for a timestamp, and that's a potentially much more useful one.
I tend to agree with you. What I try to avoid is is people being loosey-goosey about their definitions. And when someone says, talks about a timestamp, I always ask, where did it come from? And you told me this, Edward. It's like, you know, you've got to be very careful about what timeline you're using. So my conclusion in helping time, if you have to have timeouts and retries, at least do them relative to your own clock and not against some, you know, big clock in the sky that doesn't exist because you think that, you know, your local clock is disciplined by GPS or whatever else, which it's not. But if you really go to town on this and say that, by the way, an instant, you know, is impossible to define because of this pivot problem of the speed of light. But an interval is definable, and you can define a very nice interval using Kevin Stanton's clocks on the same system. And that can then, you know, project out to your cluster or your local infrastructure, you know, what the timestamp order should be, and be able to keep that consistent. So I think the meaning can be dissected. Is the meaning, is this a time interval on my timeline, or which timeline is that meaning based on? What I'm trying to say is if it's based on timestamps that were applied at distant nodes against some, you know, PTP background of time, I'm saying that that shouldn't have the meaning that we currently ascribe to it, because that's what causes the causality violations.
Yeah, I agree with that. Thanks.
I have a question, Paul.
Go ahead, Hasham.
In the paper, the Microsoft paper, I put a link to it actually. They said that using large language model is a way to address the problem of retries in traditional software design. But I don't understand how LLM can do that.
So what I'm giving is an example of the best current knowledge that we have about the nature of the problem from an engineering perspective, and a very valiant attempt by these engineers who are clearly highly skilled in this to try to solve this problem with engineering. And so my hat's off to these guys for going this far as you can. The bottom line, though, in my in estimation, is that timeouts and retry is still the root of all evil. In other words, it's better to stop doing timeout and retries and find another solution than it is to go what I call with this bang, bang, bang networking, which is what I mean is, you know, you have an imposition, you go bang, here's something, take it, swallow it. And if it can't, it has to throw it away. And if it didn't swallow it, you go again, you go bang, bang, and you send a retry. And if that didn't work, you send more retries, bang, 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 bang. So I call it bang, bang, bang networking. I'm saying, I'm trying to draw everyone's attention to the idea that if you rethink the idea of timeouts and retries, particularly when you're dealing with the meaning of this interval, on which timeline are you referring to the interval, then you will find that the problems won't go away, but they will definitely be reduced. So rethinking timeouts and retries, I think, can be done, especially as we talk about infrastructures inside a single rack or on a single large motherboard in a chiplet ecosystem.
Yeah, but I don't know how LLM will help do that.
And LLM doesn't help you.
Yeah, but this is what they said.
Well, let me tell you where it comes in. So if your assistant, which is, you know, tied into whatever is your favorite LLM, you know, is going to be giving you lots and lots of stuff. We know that it hallucinates, that we knows that it gets things wrong. We know that it can like, you know, mislead you or whatever else. So when your AI assistant from whatever vendor you prefer to use says that, okay, would you like me to go and buy you know, this particular, you know, product for you? Shall I go and research, you know, who's got the cheapest price, who's got the fastest delivery, and so on, and it will just, you know, give me the answers. Then would you tell your AI assistant to say, yes, go ahead and do that transaction for me? It could be a $10 transaction or a $100 transaction or a $100,000 transaction. My argument is that you're not going to ask your AI to probabilistically do transactions on your behalf. You're going to need a separate infrastructure that you can trust, such as the kind of things that we're discussing here at the Time of Finance project and in the Mulligan Stew meetings, which we have on Friday mornings. So Hisham, did I answer your question?
I would like to talk more to you about it.
Excellent. Okay, David, it looks like you've got something coming, a smile on your face. Go ahead, David.
Not necessarily with LLMs, but using probabilistic models to make buying decisions in which you may pay $10, you may pay 10 million. That is exactly what the global financial system is continuously doing right now. Whether that's good or not is a separate question, but when you said that, I couldn't help but smirk. Sorry.
So anyway, that's why we're doing what we're doing, and we're trying to highlight the dangers of timeout and retry. We really need to dig deeper. This paper is a great way to do it. You can, if you go to any of the large vendors, for example, we know, for example, that AWS internally, their best practice is randomizing the timeouts. That's the best they know what to do at the moment, because this is such a serious problem. All right, we've got coming up to the top of the hour, and as my CEO at Sun Microsystems taught me, I always like to close meetings down on time. So
Yes.
do we have any final questions in the last minute?
One, why do we always have this concept of you have to synchronize to a single grandmaster and apply a single timestamp? If I have 256 GNSS receivers or even direct fiber connections to every major lab, whether it's NIST, USNO, why can't I say this event, according to this grandmaster, is here, this, and this, and so there's no failover? And you just have pre-encoded logic of how to handle which ones and how to prioritize it. This concept always bugged me. We're always trying to tell to sync our systems to UTC NIST, and if we have our own atomic clocks, we could be as accurate or better.
I think, yeah, that's very similar to what I learned from Kevin. And yes, I see a great opportunity, particularly in applications where they can just they can really just give a super accurate, super reliable clock to every cluster or whatever else, and say, look, if you're responsible for all the transactions in New York, well, you better be, you can have, that infrastructure that maybe segregates by, different grandmasters by.
I'm not talking segregation, though. I'm saying get rid of the concept of any event has, quote, one time. It's a false concept. We know this. The national labs don't agree what nanosecond it is with a bunch of hydrogen.
I think that is it comes from the arbitration of accuracy. So basically, if you have a bunch of machines that they are going to work with each other, they should be in a raft. So they should have the same accuracy, and meaning the same source of accuracy for time. So they should come from the same time source.
But why does it be one source? So to me, this is always a false concept.
Because you want to have an agreement between they want to speak the same language, right?
This is the fundamental problem. We know none of these clocks are correct. So why pick one? Very fundamental.
It doesn't matter. You can have the worst clock, but I mean, you have to have it stable, because how T1, T2, T3, T4 works. You have to have it stable. As long as everyone follows that clock, everyone, right? They are speaking the same language. It's like all this different pronunciations for all these words that I'm like, why is it like this in English? Like, I mean, it's full of these, crazy spellings because someone decided to make it like this. But as long as I use the same alpha, like, the same structure, and Paul uses the same structure, and then we all have some meaning associated to that, who cares? It's arbitrary.
You don't have to pick one and stick with it. You can take all of them in and have some sort of priority encoding to say.
Yeah. You can take, and as a matter of fact, this is the approach I've been taking on our end, is like I take multiple of these clocks. Exactly. But they happen to be, and then again, there's a difference between GLONASS, Baidu, Galileo, like there's like some offsets different, but then the offset doesn't change. That's a good indication of both sides have good precision. And then I do my fusion, which is basically, my fusion is not really fusion. I just monitor them and I see, are they holding up things versus each other while they dance differently? And that comes from a covariance analysis that you look like, yeah, there's no, because the worst thing you can have is you think you are like reading 4 different sources while 3 of them are copies from one, and then let's say you care about like some further down source because you also have a bigger raft, and then all of a sudden all 4 are, you know, occluded because the source for all of them is messed up. So I mean, it's just,
Well, shouldn't we be capturing that? This is my whole problem today. We keep trying to say there is this truth, yet a lot of these talks we go through, we know this is a false concept. So just
yeah,
mark.
there is no truth. It's a convention. Convention. Yeah.
I think
right.
if I can just add a comment to that, I think I agree with Ahmad here. This is about agreement, not about statements about truth, right? If you have 2 agents who need to agree on the order in which 2 things happened,
Yeah.
you have to have some way of structuring that agreement.
Yeah.
If you just say,
But
well,
that's
the
what-
truth is fuzzy, and
But that's what
therefore
the priority
you
encoding
give
is.
up on the possibility of agreement, then,
You can have that without picking one clock and picking one time for an event.
oh, sure, there's lots of ways you could get agreement, but it sounds like the idea of picking multiple clocks is to try to get closer to some nebulous truth. But what
No,
nebulous truth is actually not well defined.
it's just saying this is the data I have. I'm not going to interpret it. I'm not going to pick a winner. Right now, for the purpose of doing a priority encoding for agreement, you have to. But otherwise, especially on the recording side of this data for audit trails of these very important systems, just don't do that. Because you're throwing away very valuable data that could be intentionally compromised by bad actors.
I agree. For that application, in recording the fuzziness of your information seems very valuable.
So like for me, the ideal would be you have a passive tap of the wires and you're also feeding in the raw GNSS waveforms as captured. So you're not discarding anything, and you have that exactly bit for bit pretty much as it's streaming down the SerDes.
But, you know, I mean, if you record that and then take action on the basis of some decision about ordering, what you've essentially done is recorded the fact that that decision was kind of arbitrary, and you've opened up a can of worms for possible, you know, contesting of the decision and so forth. This seems like a really bad idea for financial markets.
It's not arbitrary. You have a predefined encoding and scheme, but you're still capturing all of that data rather than trying to say, okay, this GNSS system or this GNSS receiver may have had some bug. Oh, well, that is the definitive truth for all of time.
I think we're saying the same thing.
I get your point.
It's like, yeah, I
Valid
mean, you're basically looking for all these different sources, and then there is no right or wrong. And as a matter of fact, there is no right or wrong. And
well, but this is what I disagree.
unless everything stays stable, we're in normal. Something changes, something changed. And
There's 2 parts of the system. One is the real-time functioning of the system. The other is I have an audit trail of incredibly valuable data, and I need it to always be as precise as possible. And if I screw it up, I can never roll back time and get that back.
That's right.
One shot to do this. And so in that case, if I can figure out 6 months from now that I'm getting multipath interference from particular satellites across the street, I can recompute time if I capture that raw data, but if and only if. This is why I hate the fact that we just read some quote definitive truth off of a PDP or a PTM daemon or a GNSS chip. We don't have data that later we actually can theoretically go back and improve and remeasure. Now, again, I have a skewed background where it's dealing with this particular stream of financial data where you really do want this truth. But to me, this has always been sort of an Achilles heel that we do in every single system that personally drives me nuts.
Yeah. All right. So I think we adjourn today, and we will have something in a week, and we'll, like, I think we have a roundtable by Rodney, and also something by like someone Hisham Hisham, what was it? Is Hisham still there? I think he's not
Hisham
there.
is still here.
Yeah, Hisham is still here. So, and we'll have also the one in 2 weeks. Let me see. This is a lot of hand waving. So basically, we have next week, December 11th, the Global Summit Roundtable summary that Rodney is going to put with something in addition that Hisham is going to put. So it's going to be most likely a 2-hour thing. Then on December 18th, we're going to have Pat Helland. He's going to give us a presentation with the title, Yours, Mine, and Ours. So looking forward to that. All right. See everyone in a week, and then also those who come on regular in 2 weeks. All right. Bye, everyone.
Hi, everyone. Thank you.
Take care, everyone. Thank you.